Hi, my name is Nathaniel Anderson, presenting for my Dynamic Team's Spring Term project, in which we explored conservation of energy and conservation momentum. So, we'll start off with a brief introduction of what exactly was our project. So, our class was tasked with determining a real world dynamics project that we would explore in groups in order to analyze and better understand a selected topic, with the ultimate goal being to see how a dynamics problem and analysis play a factor in everyday jobs, activities, and phenomena, and to better cement our knowledge base for our chosen topic by having us not only compute calculations, but by coming up with our own experimentation process and analysis. Our team decided to either prove or disprove the law of conservation of energy using real-world example of Hooke's law, kinetic energy, and potential energy. To test this, we used a 3D printed slingshot to fire a tennis ball at a variety of angles and tracking its velocity, motion, and distance with a range and velocity finder and computer software such as Logger Pro and MATLAB, and then running hand calculations to generate velocity and position time graphs in Hooke's law to determine the supposed elastic potential that the slingshot begins with. We then use these methods to see whether or not the energy is conserved in a real world example. So, how did we conduct our experiment? We began by first coming up with a design for a sling to hold our projectile and then 3D printing it in the Fab Lab. From there, we determined that we would go to the IM fields because it had the most space for us to be able to launch and would rig our elastic bands to one of the bench backings, and then use a range and velocity finder to get an instant and close measurement of the total distance and maximum velocity for each trial. We did it at both a flat angle for a datum and then an intermediary one at about 45 degrees in order to get multiple data sets and recordings to best analyze the conservation of energy and conservation momentum equations. We also decided to stage different stretch lengths on the ground in order to standardize our launches and to be able to better analyze how Hooke's law and the spring constant come into play. In order to make sure that our measurements were consistent, we had each of the three launches done for the angled and flat test performed by the same individual with roughly the same angle and drawback. We marked the starting launch position, and after firing, one of the team members would measure from the launch to the point of first impact, with another team member standing about 20 paces back to record video for each trial. That was then loaded into Logger Pro to determine the definite values of important components such as initial velocity, final velocity, and maximum height. MATLAB also allowed us to use the exact potential and kinetic energies of the tests to compare with our hand calculated values of our theoretical problem to determine the accuracy of real life applications. So, how did we record our experiment? We did so by taking pictures and videos, and here are some of the pictures taken, with the leftmost one being of our slingshot setup, our middle one being of the marked drawback positions, and then right one being of an example of how we would launch. And next we have a brief video of one of our launches and how we would record.
Talking.
So from there, we took these values and put them into Logger Pro and MATLAB, and also did hand calculations to have a secondary computation to compare to. And from here, you can see all of our box answers are the approximate angles and distances, along with our kinetic energies and spring constants. And then here are our MATLAB and Logger Pro graphs of our marked potential and kinetic energies during our flat and then angled launches. And then from there, we decided to come up with our findings. So we determined that from our experimental values and theoretical problem, we can see that our collected data could in fact be transcribed into a theoretical perfect dynamics problem with outside forces being negligible. It was also concluded that gathering methods such as MATLAB and Logger Pro can be translated from a real world situation to usable values for theoretical problems and also physical ones. And our hand calculations compared with our computer calculations were only off by a factor of around 15%, which was well below our threshold of rejection. And so, what are some of our closing thoughts and a summary of our project as a whole? Our team concluded that whenever it comes to the comparison of real world examples and idealistic problems in regards to conservation of energy, they can be equated using both collected values and computationally with online solutions. Minute factors such as air resistance, differing launch trajectories, and changes in spring constants of elastics used can also be added for a greater measurement of accuracy, but ultimately can be disregarded in small scale cases such as our experiment, where the margin of error is not necessarily of great importance. Um, in regards to our project as a whole, we all agreed that this was a fun and interactive project that bolstered our overall understanding of both conservation of momentum and conservation of energy, along with spring constants as a whole. Thank you. If you have any questions or comments, feel free to talk to one of our group members after class or shoot us an email at our UGA emails. Um, and again, I was Nathaniel Anderson with our team's spring term project. I was also aided by Andrew Carver, Ryan Formel, and Jackson Knecht. Thank you.